Hello, alright, the problem of the week, number 4. I guess we should call them problem of the month now. Anyway, this problem, the first parts, like part A, most people did pretty well, but I'd like to walk through them really quickly. But by the time we got to part C, things started to get a little shaky, and so I'm going to take a look at the first bits. What they're trying to do is to follow you through some exploration. First, what they're ultimately trying to do is to get me to figure out the area between the two curves that are shown. So here's a curve, which is actually a line, and here's another curve, and ultimately my goal is to find the area that's bounded by those two functions. But instead of making you dive into the swimming pool headlong, they're trying to scaffold so that you can actually so that you don't skip some parts of the analysis that are required to be successful here. So, starting off with the first bit, they're saying, okay, well, let's start with k, since it can be any real number, let's start with k equals 0, a really simplistic case. That means that the first function is x e to the x, like it always will be, and the second function is just y equals 0. You can see in the graph that the intersection of y equals 0 with the function curve is only at 0, 0, since the function curve is asymptotic. But we can analytically prove this by setting the two equal to each other. In order for x times e to the x to equal 0, either x has to equal 0 or e to the x has to equal 0, which doesn't happen. And therefore, the only point of intersection when k equals 0 is going to be at the origin. So that's simple enough. Most people nailed that bit. Part 2 said to find the angle of the tangent to the curve at the point of intersection, which is at the point 0, 0. So I have to first find the rate of change. So I take the derivative of the function, and most people, again, nailed this pretty well. I factored it out so it makes it easier to substitute when I substitute in 0 for x, and I end up with 1 times 1. The slope of the line is 1. Point on the line is 0, 0, therefore y equals x is the tangent line. We all know that the angle already is 45 degrees, or pi over 4, but it doesn't hurt to draw a quick sketch illustrating a line with a slope of 1 is a 1-to-1 ratio of legs, and therefore we have pi over 4, or 45 degrees, just for a complete workup. And we can see the tangent line here. Because of the scale, it looks a little steeper than it is. Alright, next issue. If k equals 1, show that the line is tangent to the curve. It's pretty interesting that they asked this question the way they did, because most people, when they're trying to find the angle of intersection between the line and the tangent line, would find y equals x already. So we already know it's the tangent line. But what I want to do to prove it is, we can actually show that x is equal to x times e to the x when k equals 1. Find the intersections, which is a factored expression now, and we get x equals 0, or 1 minus e to the x equals 0. When we solve this, we end up with x equals 0 as well. So the two solutions are one and the same. So when k equals 1, the tangent line is the line y equals x. So there's only one intersection at the origin. So they're telling you all of this information just so that you can do part C. So at the beginning of part C, in order for us to find the area between two curves, we need to be able to find out where they intersect at two distinct points. The problem already helped us out, or so the way the problem was asked helped us out, because now we understand that if k equals 0, we're only going to have one intersection, so we can't find the area between two curves. And if k equals 1, we're only going to have one intersection, so we can't find the area between two curves. All the other options available for k in the real number set we have to consider. So, first thing we do is we set the two equations, y equals kx and y equals x e to the x, equal to each other to find the x coordinate for intersection. So when these things are equal, I'm going to subtract kx from both sides so that I can get use the zero product principle. I factor out the x and I get these two conclusions. Either x equals 0 or e to the x equals k. In other words, x equals the natural log of k. So here's where things start to get interesting. Natural log of k could be positive, or the natural log of k could be negative, and that's going to affect what our area curve equation is going to be. You'll see what I mean in a moment. It's asking us to find the values of k for which there are two distinct points. So when k equals 1, it's not going to work. We've just proven that over here, but just as a reminder, when k equals 1, x is the natural log of k, which is 0, which means we have two of the same solution, a double root, if you will. Now, if k is negative, we really can't find two distinct points because the logs of negative numbers do not exist. Graphically speaking, if k was negative, then the function would go in this direction, and it would still only cross at the origin and no other place. So we put all that information together, and we end up with the fact that in order to get an area between two curves, we can only explore positive k values except k equals 1. Alright, now, it said write down the coordinates of the points of intersection. It said write down, which means you can do this in your head, but just to say what's in my head, so if I could tell you, anyway, just kidding, is e to the natural log of k, which is just k, so it ends up being k times the natural log of k, is the y value. So the point of intersection, when we have two unique intersection points, the functions will intersect at 0, 0, and natural log of k, comma, k natural log of k. That creates two unique scenarios. If k happens to be bigger than 1, then the natural log of k is going to be positive. If the natural log of k is positive, then we're going to have intersections to the right of the origin, and that's going to give us one area algorithm, because the natural log of k being bigger than 0. However, if k happens to be between 0 and 1, the natural log of k turns out to be negative. And if the natural log of k is negative, then our point of intersection is to the left of the origin. So, to account for the area between two curves, we can simplify by using absolute values. By using absolute values, we don't have to worry about our boundaries being bigger or smaller. This is based on the principle that if I take the integral from a to b of f of x dx, that would be equal to the integral, the opposite of the integral from b to a of f of x dx. So, with all that in mind, I'm going to have opposites depending on whether the natural log of k is less than 0 or greater than 0. So to account for the potential of opposites here, I'm using absolute value. That will give me areas between the curves, and then the other thing I should do here is I should specify for k greater than 0, less than 1, or k greater than 0, or greater than 1. So, that's the integral. I can put that into a graphic calculator and it will, or any sort of software, and it'll give me values for areas regardless of the value of k, as long as it's within the expected domain. So, moving on then, we're going to have to actually integrate here. And so the first thing we know, we have the coordinates of their intersection points. We have the area statement right here. And now we actually have to calculate the area when k happens to be between 0 and 1. So looking back at our picture here, we're going to be finding the area in this area, or in this place. So the first thing we got to do is recall that the natural log of k is going to be smaller than 0, so if we don't want to worry about absolute values and negatives, let's put the natural log k as the left bound and 0 as the right bound, and that way we will have a positive area when we're done. So, now I have to examine the integral of the difference between the two curves. And with the difference between two curves here, we can actually separate into two integrals. This one is easy to integrate because it's with respect to x, that's just a simple linear into quadratic. Here, however, I have a product, and every time I see a product of two functions, the first thing I have to think of is integration by parts. Just remember, integration by parts comes from the reversal of the product rule, and then we reshuffle it a little bit. And so we have the four parts. We have the u, the v prime, the v, and the u prime. And what we have to do is make sure we establish u and v prime to be one of these two functions. So recall, I'm going to choose u to be x because its derivative becomes more simple. I'm going to choose dv to be e to the x because it's really easy to integrate and turns out to be the same thing. So, put all these pieces together, we integrate kx dx, that's just going to be half k times x squared. And now by integrating by parts, we're going to have, hold on, we have the u times the v, which is the x times the e to the x, biggity blam. And then we're going to subtract the integral of 1 times e to the x, that's over here, dx. On you go. The integral of e to the x is e to the x, plus, don't forget our constant. We can distribute the negative, the constant we can still leave positive, doesn't matter. And if we want to, we could factor out the e to the x. It might be easier to work with this equation. So I have pre-integrated this particular function to be this strange looking thing where it's half of k x squared minus e to the x, x minus 1, plus a constant. That constant won't be an issue though, because we're finding a definite integral. I use my brackets and put in the integral that we just found with the boundaries. Of course, then we substitute in 0 for x, and we subtract what happens after we substitute in natural log of k for x. This again represents the area between the two curves. Now, all inside of here, all up in here, we have, this is going to be the negative 1, which is e to the 0, times negative 1. Negative 1 times negative 1 is 1. And of course, this part zeroes out. Now we have to take care of the rest of it. We're going to subtract k over 2 natural log of k squared minus k natural log of k plus k. Okay? Now, what to do with this is really a problem because k is, any number between 0 and 1. So we know k is a positive number. But my challenge here, if I remember correctly, if I can go back and see the question, I'm trying to show that the area, not only what the area is, but for any values of k between 0 and 1, that the area is going to be smaller than 1. Now, if I go back and look at my integral, oh my, right there, I have 1 minus stuff. Now here's the issue. If this stuff happens to be negative, then I'm going to have 1 minus a negative number, thus the area is going to be greater than 1. In order for the area to be less than 1, all of the stuff inside the brackets has to be positive. So it's up to me now to prove that any k between 0 and 1, when substituted into this expression, is going to turn out to be a positive number. I hope you see the problem. If I actually put in a value of k, I'm going to be subtracting something here. Now we can use intuition and say that this is all positive right here, and k is a positive number because it's 0 and 1 here, and then here the natural log of k is negative. Negative times a negative is a positive. So we can state that all of this stuff is going to be positive, but it might be easier to show by just doing a little bit of quadratic trickery. The first thing I'm going to do is factor out the k over 2. Once the k over 2 is factored out, then I end up with an expression that looks very quadratic-y. And I'm thinking to myself, if only I could complete the square for this guy, I would actually have a squared number, which is always positive. So I factored out the k over 2, and now I'm going to kind of sort of complete the square using a little bit of divine intuition. I know that this stuff right here is a perfect square because I've seen it before. This is like a squared minus 2ab plus b squared. So that's our perfect square already built in. So all I did was separate the 2 into the 1 and the 1 so that this can be factored as a perfect square, and then the extra plus 1 is added. So basically, this is the chunk that I want to prove is positive, and it's real easy to do because all that chunk is b. b is definitely positive because a, k over 2 is positive because k is between 1 and 0 already. This is a perfect square, so that's always positive. And then we add 1, we'll be adding to a positive number. Since b, this chunk of stuff here, is bigger than 0, or always positive, when I take the area 1 minus a positive number, I'll always be less than 1, or McGurr. Hope this was helpful. Sorry it was long. Have a good day.